February 18, 1918. Colorado Fuel and Irons Limestone Quarry. The morning inspection report from visiting European metallurgists would never fully capture what they witnessed cutting through granite that day. American bulldozer blades, made from steel that defied everything European materials science said was possible for heavy equipment. Through the dust and roar of the Rocky Mountain quarry, identical manganese steel blades pushed through rock with efficiency that seemed impossible to European observers. No frequent replacements, no predictable wear patterns, no 2,000-hour service limits. Yet they cut granite with consistency that European carbon steel blades could never match. In European quarries, standard bulldozer blades required replacement every few months. Each blade followed predictable failure patterns, steady wear, declining performance, inevitable replacement cycles. Most carried operational costs that made large projects barely profitable. The Americans were operating with metallurgical philosophy the Europeans had dismissed as theoretically impossible. Work-hardening steel, self-sharpening edges. 15-year service life pushing the hardest rock formations. 4,000 miles from European steel mills, the most decisive materials breakthrough in construction history was revealing itself. Not in superior manufacturing, not in premium alloys, but in the counterintuitive science that made American steel stronger under punishment in ways European metallurgy never imagined possible. The steel foundries of East Peoria hummed with unprecedented activity in the autumn of 1916, their smokestacks painting the Illinois sky with the dark signatures of American industrial ambition. Inside Caterpillar's engineering offices, the morning light filtered through windows already clouded with metal dust, illuminating technical drawings that challenged every established principle of bulldozer blade construction. Robert Morrison stood before a conference table crowded with metallurgical samples, his calloused hands moving between chunks of carbon steel and experimental manganese alloys, while Frank Whitney nervously adjusted his spectacles and calculated costs that made his stomach tighten with each decimal point. The numbers sprawled across Whitney's ledger told a story of European dominance that had persisted for decades. Standard bulldozer blades manufactured according to British specifications contained 0.4% carbon content, achieving 260 Brunel hardness through conventional heat treatment methods that Sheffield Steelworks had perfected over 3 generations of metallurgical refinement. These blades operated within predictable parameters, steady wear rates, scheduled replacement cycles, operational costs that construction companies could budget with mathematical precision. European engineering doctrine had established these specifications not through experimentation, but through accumulated wisdom, each number representing thousands of hours of field testing across quarries, railroads, and mining operations that stretched from the Scottish Highlands to the German Ruhr Valley. Professor Heinrich Krüger's latest technical bulletin lay open beside Whitney's cost projections, its precise Germanic sentences delivering devastating critique of American metallurgical experiments with the authority of 40 years spent perfecting European steel science. Krüger had built his reputation on systematic analysis, methodical testing, and unwavering adherence to proven principles that treated each deviation from established practice as dangerous gambling with worker safety and corporate resources. His assessment of manganese steel carried the weight of institutional knowledge. Work-hardening properties were temporary phenomena, catastrophic failure remained inevitable, and American claims of 15-year blade life violated fundamental materials science that European universities had taught for generations. Morrison studied the manganese steel sample in his palm, feeling the deceptive softness of austenitic structure that would transform under impact stress in ways that traditional metallurgy textbooks claimed impossible. The steel began its service life at 220. Brunel hardness, softer than mild structural steel, yet Morrison understood the crystalline dynamics that would occur when this material encountered the compressive forces of granite pushing. Each impact would create twinning structures within the austenitic matrix, strain-induced hardening that increased strength rather than diminishing it, metallurgical behavior that challenged every assumption about steel performance under punishment. The chemistry required precision that made Whitney's cost calculations increasingly grim. 12 to 14% manganese content 1 2/10% carbon, heat treatment at 1900 degrees Fahrenheit, followed by immediate water quenching to preserve the austenitic grain structure that made work hardening possible. Each temperature variation of 25 degrees could ruin the metallurgical transformation, creating brittle carbide formations that would crack under the first serious impact. Worse yet, the steel became unmachinable after heat treatment, requiring blade shapes to be cast with final dimensions rather than machined to specification, manufacturing complexity that European suppliers exploited to undercut American bids by 15% on major construction contracts. Tommy Kowalski emerged from the foundry floor with molten metal still glowing on his leather apron, his Polish-American directness cutting through the technical discussions that had consumed the morning meeting. He had watched Morrison work the furnaces personally, earning respect through shared sweat and demonstrated understanding of practical metallurgy that separated theoretical engineers from those who truly comprehended steel behavior. Kowalski's foundry experience told him that Morrison's temperature control methods could work, but the economic pressures surrounding experimental blade production threatened steady employment for workers whose families depended on Caterpillar's expanding operations during America's industrial surge. The Missouri Pacific Railroad contract represented stakes that extended far beyond metallurgical theory. 2,400 miles of roadbed construction worth $2 3/10 million, earth-moving operations that would test American engineering capabilities against European competitors who had dominated global infrastructure projects for decades. Standard carbon steel blades lasted 180 hours before replacement became necessary, operational limitations that made large-scale construction projects marginally profitable and vulnerable to foreign underbidding. Morrison's experimental manganese blades promised revolutionary economics, initial costs 340% higher than conventional steel, but service life that could extend beyond 15 years of continuous rock pushing. Whitney understood the broader implications that made this metallurgical experiment a test of American industrial credibility. European steel companies had built their dominance through institutional knowledge, systematic testing, and manufacturing processes refined across generations of gradual improvement. American innovation represented a different approach, bold experimentation, willingness to challenge established doctrine, and confidence that superior understanding of scientific principles could overcome traditional methods through breakthrough rather than incremental advancement. The manganese steel blades would either vindicate American metallurgical science or provide European critics with devastating evidence that colonial engineering lacked the disciplined methodology necessary for reliable heavy equipment. Morrison's quiet confidence radiated from years spent studying crystalline structures and thermal dynamics, theoretical knowledge combined with intuitive understanding of how metals behaved under stress conditions that laboratory testing could never fully replicate. His Scottish father's stories of immigrant workers dismissed as intellectually inferior had instilled determination to prove that American innovation could surpass European tradition through superior science rather than marketing claims. The manganese steel experiment represented more than improved bulldozer blades. It embodied the thesis that American engineering excellence emerged from understanding the fundamental reasons behind metallurgical behavior, transforming industrial competition from craft tradition to scientific mastery. The East Peoria foundry transformed into Morrison's personal laboratory as October's crisp air carried the acrid smell of experimental metallurgy through the industrial district. Standard furnaces. Designed for conventional carbon steel casting, proved inadequate for the thermal demands of 12-foot manganese blade production, their temperature variations creating metallurgical chaos that ruined entire batches of expensive experimental steel. Morrison spent sleepless nights redesigning furnace architecture, developing continuous feed systems that could maintain 1900 degrees Fahrenheit within 25-degree tolerances across the entire length of massive blade castings that weighed nearly 800 pounds each when complete. Tommy Kowalski worked alongside Morrison through 16-hour shifts, their partnership bridging theoretical metallurgy with practical foundry expertise as they modified burner configurations and airflow patterns to achieve uniform heating that European foundries had never attempted on such massive manganese steel components. The Polish-American foundryman's intuitive understanding of molten metal behavior complemented Morrison's scientific training, creating collaborative innovation that combined immigrant work ethic with formal engineering education in ways that challenged traditional hierarchies between management and labor. Kowalski could detect thermal problems through subtle changes in furnace sound and flame color that instruments failed to register, practical knowledge that proved essential when working with metallurgical processes that existed at the cutting edge of industrial science. The first trials produced disasters that validated European skepticism about American experimental methods. 12 blades cracked during the quenching process, as rapid cooling created thermal shock that fractured the austenitic structure Morrison had worked so carefully to achieve. The manganese steel's unique properties demanded cooling techniques that standard foundry practices could not accommodate. Water circulation systems designed for carbon steel proved inadequate for managing the thermal stresses that occurred when massive castings transitioned from 1900-degree molten state to room temperature within minutes. Each failure represented thousands of dollars in wasted materials and labor, costs that made Whitney increasingly nervous about the experimental program's impact on Caterpillar's quarterly profits during a period of rapid corporate expansion. Morrison analyzed each fractured blade with scientific methodicality, mapping crack patterns and measuring grain structures to understand the metallurgical forces that caused experimental failures. The solution emerged through systematic study of thermal dynamics, controlled water circulation combined with modified blade geometry that distributed cooling stresses more evenly across the massive steel castings. The breakthrough came when Morrison realized that manganese steel's austenitic transformation required different cooling rates for different sections of the blade, variable quenching that allowed the cutting edge to achieve proper hardness, while preventing thermal shock in thicker structural sections. November brought incremental progress as Morrison's modified quenching techniques produced blades with intact metallurgical structure, their austenitic grain patterns displaying the uniform characteristics necessary for proper work-hardening behavior under impact stress. The steel emerged from heat treatment with deceptive softness, 220 Brinell hardness that made the blades appear inferior to conventional carbon steel until subjected to the compressive forces that would trigger their remarkable transformation. Morrison documented each successful casting with meticulous precision, recording furnace temperatures, cooling rates, and metallurgical analysis that would provide the scientific foundation for revolutionary manufacturing processes. December's bitter Illinois winds carried the sounds of successful blade production as Morrison's team achieved consistent results with their experimental techniques. The continuous feed furnaces operated with precision that European foundries had never attempted, their temperature control systems maintaining metallurgical conditions across 12-foot blade lengths that traditional casting methods could not accommodate. Each successful blade represented mastery of thermal dynamics that challenged established European doctrine about the practical limitations of manganese steel manufacturing on industrial scales, necessary for major construction projects. Frank Whitney watched the experimental program with growing confidence as production costs stabilized and quality control improved through Morrison's systematic approach to metallurgical innovation. The initial disasters had been expensive lessons, but the emerging consistency suggested that American engineering methods could indeed surpass European techniques through superior understanding of scientific principles rather than adherence to traditional practices. Whitney began calculating the economic implications of successful manganese blade production, manufacturing costs that remained significantly higher than conventional steel, but potential service life that could revolutionize the economics of earth-moving equipment across the construction industry. The foundry workers developed expertise in metallurgical processes that existed nowhere else in American industry, their practical knowledge of manganese steel behavior creating competitive advantages that European manufacturers could not easily replicate. Morrison's willingness to work alongside foundry labor, sharing both the physical demands and intellectual challenges of experimental metallurgy, created collaborative relationships that transcended traditional management hierarchies. The success of the experimental program depended not just on theoretical understanding, but on practical skills that could only be developed through hands-on experience with the unique properties of work-hardening steel. By December's end, Morrison's team had produced blades with perfect austenitic grain structure, tough, ductile castings ready to demonstrate their remarkable transformation under the punishing conditions that would test American metallurgical innovation against European skepticism. The steel appeared deceptively ordinary in its initial state, soft enough that conventional hardness testing suggested inferior performance compared to traditional carbon steel blades. Yet Morrison understood the crystalline dynamics that would occur when these experimental blades encountered the granite formations of Colorado's testing grounds, metallurgical transformation that would either vindicate American engineering science or provide European critics with devastating evidence of colonial industrial inadequacy. The foundry's success represented more than improved manufacturing techniques. It embodied American confidence that superior scientific understanding could overcome traditional European methods through breakthrough innovation rather than incremental refinement of established practices. The Colorado Fuel and Iron Limestone Quarry stretched across the foothills like a wound carved into the Rocky Mountain landscape, its terraced walls exposing granite formations that had tested earth-moving equipment since the mining boom of the 1880s. January's bitter wind carried the diesel exhaust and rock dust that marked serious industrial operations, while Morrison's experimental manganese blades prepared to face the ultimate metallurgical examination against stone that registered 2,400 pounds per square inch compressive strength. The quarry's foreman, a weathered veteran of Colorado mining operations, watched skeptically as Caterpillar's prototype bulldozer positioned itself before granite outcroppings that had worn out dozens of conventional carbon steel blades over the previous year. Morrison stood beside the massive earth-moving machine, his breath visible in the thin mountain air as he examined the manganese steel blades that represented months of foundry experimentation and metallurgical innovation. The steel appeared deceptively soft in its initial state, 220 Brinell hardness measurements that made the blades seem inferior to conventional equipment until subjected to the punishing impacts that would trigger their remarkable transformation. Standard carbon steel blades typically lasted 180 hours in these granite conditions before replacement became necessary, operational limitations that made large-scale quarrying barely profitable and vulnerable to equipment failures that could shut down entire mining operations for days, while replacement parts arrived from distant suppliers. The first day's operations revealed the counterintuitive nature of work-hardening metallurgy, as Morrison's experimental blades began their service life performing no better than conventional steel, their soft austenitic structure yielding to granite. Impacts without the immediate superior performance that traditional blade improvements typically demonstrated. Quarry operators expressed doubts about American experimental methods as they watched expensive manganese steel blades struggle through initial cutting operations with efficiency that seemed to validate European skepticism about untested metallurgical innovations. The steel's 220 Brinell hardness provided little advantage over standard carbon blades during these early hours, creating concerns that Morrison's theoretical understanding of work hardening had failed to translate into practical quarrying advantages. Yet something remarkable occurred as the blades accumulated impact hours against Colorado granite. Each strike against rock created microscopic deformation within the austenitic matrix, twinning structures that increased hardness through strain-induced transformation rather than the gradual wear degradation that characterized conventional steel behavior. Morrison documented these metallurgical changes with scientific precision, measuring hardness increases that defied traditional materials. Science expectations. By the second week of operations, blade edges had reached 320 Brinell hardness, surpassing the original strength of conventional carbon steel through punishment rather than despite it. The transformation accelerated as operational hours accumulated, and impact forces continued reshaping the manganese steel's crystalline structure. 200 hours into the testing program, blade edges measured 380 Brinell hardness while maintaining sharp cutting geometry that conventional blades had lost through predictable wear patterns. The quarry operators began reporting unprecedented performance characteristics, rock cutting that improved rather than deteriorated over time, blade edges that seemed to sharpen themselves through use, metallurgical behavior that contradicted every assumption about steel degradation under continuous impact stress. 500 hours of granite pushing revealed the full extent of Morrison's metallurgical breakthrough as hardness measurements reached 450 Brinell, harder than tool steel, and still increasing with each day of punishing quarry operations. The manganese blades cut through granite formations with efficiency that made experienced operators question their understanding of earth-moving equipment capabilities. Rock that had required multiple passes with conventional steel blades yielded to single cuts from work-hardened manganese edges, productivity improvements that transformed quarrying economics by reducing both operational time and fuel consumption during heavy excavation projects. Morrison's scientific documentation captured the progression of work-hardening transformation, with measurements that would revolutionize metallurgical understanding across American heavy industry. The steel's austenitic structure responded to impact, stress, by creating twinning formations that increase strength exponentially rather than following the linear degradation curves that European engineering textbooks described for conventional materials. Each granite strike added to the cumulative hardening effect, building cutting-edge durability that surpassed original blade specifications through service rather than manufacturing processes. The quarry's productivity statistics validated American metallurgical innovation with numbers that European competitors could not dismiss as experimental marketing claims. Standard carbon steel blades required replacement every few months, creating operational disruptions and replacement costs that made large quarrying projects marginally profitable. Morrison's manganese blades operated continuously through Colorado's harsh winter conditions, maintaining cutting efficiency while accumulating impact hours that would have destroyed conventional equipment multiple times over. The economic implications extended beyond blade replacement costs to encompass reduced downtime, improved productivity, and operational reliability that made American earth-moving equipment superior to European alternatives. Word of the Colorado testing results spread through American heavy industry like wildfire, carried by quarry operators whose practical experience validated Morrison's theoretical claims about work-hardening metallurgy. The manganese blades had survived conditions that typically consumed conventional steel within months, demonstrating operational longevity that challenged fundamental assumptions about equipment maintenance cycles and replacement schedules. Morrison's documentation provided scientific proof that American metallurgical innovation had achieved breakthrough performance through superior understanding of crystalline behavior rather than incremental improvements to established European techniques. By spring, the experimental blades showed no signs of conventional wear degradation, despite accumulating impact hours that would have required multiple carbon steel replacements. The work hardening continued building cutting-edge durability that promised operational lifespans measured in years rather than months, metallurgical achievement that represented the decisive moment when American engineering science surpassed European industrial tradition through revolutionary understanding of materials behavior under extreme conditions. The cable from London arrived at Caterpillar's East Peoria headquarters on a gray March morning in 1917, its terse language carrying the institutional weight of European metallurgical authority that had dominated global steel specifications for over a century. Sir Edward Thornwell's message demanded immediate suspension of American manganese blade production pending comprehensive safety investigation by the Royal Society's Materials Committee, citing preliminary reports of crystalline instability that posed catastrophic risks to equipment operators and construction workers across American industrial sites. The British metallurgist's concerns carried particular urgency given his 4 decades of experience with materials failure analysis and his reputation for identifying metallurgical problems that younger engineers had overlooked during their enthusiasm for experimental techniques. Professor Heinrich Krüger's technical bulletin arrived simultaneously through academic channels, its systematic demolition of American work-hardening claims presented with Germanic precision that made Morrison's Colorado testing results appear dangerously misleading. Krüger's analysis focused on the fundamental thermodynamics of austenitic steel behavior under varying temperature conditions, mathematical calculations that predicted brittleness, transitions at sub-zero temperatures where manganese steel's crystalline structure would transform from tough austenite to fragile martensite without warning. The Sheffield professor's critique gained credibility through detailed references to European testing programs that had evaluated similar manganese compositions during the previous decade, studies that documented catastrophic failures when work-hardened steel encountered thermal stresses beyond carefully controlled laboratory conditions. The European counterattack intensified when German steel cartels announced price reductions of 25% on conventional carbon blade exports to American construction companies, subsidized dumping designed to undercut Morrison's experimental program before manganese steel technology could establish market penetration. These economic pressures coincided with systematic propaganda campaigns that portrayed American metallurgical experimentation as reckless gambling with worker safety. Technical claims supported by carefully selected data from early manganese steel failures that had occurred during European testing programs in the 1890s. The German strategy recognized that successful American work-hardening technology would revolutionize global earth-moving equipment, threatening European industrial dominance in heavy machinery markets that had generated substantial export revenues for decades. British technical journals published devastating analyses of American blade testing that questioned Morrison's experimental methodology and highlighted the limited temperature range of Colorado quarry operations. Sir Edward Thornwell's critique gained particular attention when he demonstrated that manganese steel's austenitic structure became increasingly brittle as temperatures dropped below 10 degrees Fahrenheit, metallurgical behavior that American testing had never evaluated despite widespread construction activity in northern climates where winter temperatures routinely reached -20 degrees or lower. The British analysis suggested that Morrison's work-hardening success represented narrow performance under ideal conditions rather than the revolutionary breakthrough that American industrial leaders claimed for their experimental technology. European competitors understood the strategic implications of American metallurgical success with clarity that motivated systematic efforts to discredit manganese blade technology before it could establish credibility in global markets. Successful work-hardening steel would enable American construction companies to bid competitively on European infrastructure projects, threatening established relationships between continental engineering firms and traditional British steel suppliers. The technology's potential impact extended beyond earth-moving equipment to encompass railway construction, mining operations, and harbor development projects where superior blade longevity would provide decisive cost advantages over conventional European steel specifications that had dominated international construction for generations. Morrison found himself defending experimental results against critics whose metallurgical expertise commanded respect throughout American industrial circles, technical challenges that questioned both his theoretical understanding and practical testing methods. Thornwell's low-temperature brittleness predictions carried particular weight because they addressed operational conditions that Colorado testing had not encountered, highlighting potential failure modes that could validate European warnings about untested American innovation. The British metallurgist's mathematical analysis of austenitic transformation provided scientific foundation for concerns about catastrophic blade failure during winter construction operations, technical arguments that resonated with American construction executives who feared liability exposure from equipment failures during major infrastructure projects. Frank Whitney watched nervously as European criticism gained traction among Caterpillar's customers, construction companies whose confidence in experimental blade technology wavered under sustained technical assault from established metallurgical authorities. The Missouri Pacific Railroad contract remained vulnerable to cancellation if European competitors could demonstrate superior reliability through conventional carbon steel technology that avoided the uncertainties associated with untested work-hardening innovations. Whitney calculated the financial implications of losing credibility in international markets where European engineering firms possessed institutional relationships built over decades of reliable performance with traditional steel specifications that had proven their worth through extensive field experience. The German price offensive created immediate pressure on American construction budgets as conventional carbon blades became available at costs that made Morrison's expensive manganese technology appear economically unjustifiable, regardless of potential longevity advantages. European suppliers leveraged their manufacturing economies and government subsidies to offer replacement blade programs that guaranteed availability and performance according to specifications that construction executives understood from years of successful operations. These economic pressures, combined with technical criticism, to create market resistance that threatened to strangle manganese steel technology before American industry could demonstrate its revolutionary capabilities under diverse operating conditions. Tommy Kowalski expressed growing concerns about job security as European competition intensified and Caterpillar management questioned the wisdom of continued investment in experimental metallurgy that faced sustained attack from recognized authorities in materials science. The foundry workers who had developed expertise in manganese steel production found their specialized skills increasingly marginalized as company executives considered retreat to conventional blade manufacturing that offered predictable costs and established market acceptance. Morrison realized that European competitors had transformed metallurgical debate into economic warfare designed to eliminate American innovation before it could challenge traditional industrial relationships that favored established continental steel producers over experimental colonial technology. The Missouri Pacific Railroad construction site stretched across frozen Nebraska prairie, where February winds drove temperatures to minus 23 degrees Fahrenheit, conditions that transformed the massive earth-moving operation into a proving ground for metallurgical theories that had never been tested under such extreme thermal stress. Morrison's experimental manganese blades had performed flawlessly through months of Colorado quarry operations, but the brutal Great Plains winter presented environmental challenges that European critics had predicted would expose fatal flaws in American work-hardening technology. The railroad's chief engineer watched nervously as Caterpillar bulldozers prepared to push frozen soil that had hardened into granite-like formations, construction work that could not be delayed despite weather conditions that pushed both equipment and materials beyond their designed operational limits. The catastrophic failure occurred without warning during routine grading operations when the lead bulldozer struck a buried boulder concealed beneath 3 feet of frozen earth. The manganese blade split along an 8-foot length with a crack that echoed across the construction site like rifle fire, sending fragments of work-hardened steel spinning through the frigid air while the massive machine ground to an emergency stop. The failure was spectacular in its completeness. The blade that had survived thousands of impact hours against Colorado granite disintegrated under conditions that Sir Edward Thornwell had predicted with mathematical precision in his technical bulletins warning about austenitic brittleness at sub-zero temperatures. Morrison arrived at the failure site within hours, his breath forming ice crystals as he examined blade fragments that told a devastating story of metallurgical inadequacy under extreme operating conditions. The fracture surfaces revealed brittle failure patterns that contradicted everything his Colorado testing had demonstrated about manganese steel's superior toughness and impact resistance. Temperature measurements confirmed the worst fears. Ambient conditions of minus 23 degrees had transformed the austenitic steel structure into brittle martensite that shattered like glass under the impact forces that work-hardened steel was supposed to absorb and convert into increased strength through strain-induced hardening. The investigation revealed systematic flaws in Morrison's experimental program that European critics had identified through decades of materials testing under diverse environmental conditions. Manganese steel's austenitic structure remained stable and tough at moderate temperatures, but the crystalline transformation that occurred below minus 10 degrees created brittleness that made catastrophic failure inevitable under heavy impact loading. Morrison's Colorado testing had never encountered these extreme conditions, creating false confidence in metallurgical properties that proved adequate only within narrow temperature ranges that excluded much of American construction activity during winter months. Frank Whitney received the failure report with growing dread as he calculated the financial and reputational consequences of spectacular equipment failure during a high-profile railroad construction project. The Missouri Pacific contract represented Caterpillar's largest earth-moving commitment, $30,000 worth of daily construction activity that ground to a halt while replacement blades were expedited from conventional steel suppliers who could meet emergency delivery schedules. The dramatic blade failure provided European competitors with devastating evidence that American experimental metallurgy sacrificed proven reliability for marketing claims that could not withstand real-world operating conditions across diverse climatic environments. European technical journals seized upon the Nebraska failure as vindication of systematic warnings about untested American innovation that endangered worker safety and construction schedules through inadequate materials testing. Sir Edward Thornwell's analysis gained immediate credibility as his temperature-related brittleness predictions proved devastatingly accurate, demonstrating that established European metallurgical science had identified failure modes that American experimenters had overlooked in their enthusiasm for revolutionary claims. The British metallurgists' mathematical models of austenitic transformation provided scientific foundation for European superiority in materials engineering, institutional knowledge that protected continental steel suppliers from colonial competition through superior understanding of metallurgical behavior under extreme conditions. Construction industry publications amplified European criticism with editorial commentary that portrayed Morrison's experimental program as dangerous departure from proven engineering practices that had built America's infrastructure through reliable adherence to established specifications. The Nebraska failure represented more than equipment breakdown. It symbolized the risks associated with abandoning traditional European steel science in favor of untested American theories that promised revolutionary performance but delivered catastrophic results when subjected to real-world conditions that exceeded laboratory parameters. Industry executives questioned whether American metallurgical innovation could match European institutional knowledge that had developed through generations of systematic testing and gradual improvement of established techniques. Caterpillar management faced immediate crisis as construction companies canceled manganese blade orders and returned to conventional carbon steel suppliers whose products offered predictable performance, according to specifications that had proven their reliability through decades of successful field operations. The company's stock price dropped 12% within a week, as investors recognized the financial implications of failed experimental programs that had consumed substantial development resources without producing commercially viable technology. Frank Whitney confronted the possibility that Morrison's metallurgical breakthrough had become a corporate liability that threatened Caterpillar's reputation for engineering reliability in earth-moving equipment markets dominated by conservative customers who valued proven performance over innovative claims. The legal implications multiplied as Missouri Pacific's attorneys examined contractor liability for equipment failures that had disrupted construction schedules and endangered worker safety through the use of inadequately tested experimental technology. The railroad's insurance company launched investigation into whether Caterpillar had misrepresented the operational capabilities of manganese steel blades, potential litigation that could result in substantial financial penalties and contractual cancellations that would devastate the company's market position in heavy construction equipment. The Nebraska failure had transformed Morrison's metallurgical innovation from breakthrough technology into legal liability that threatened to bankrupt the experimental program and destroy American credibility in international earth-moving markets. Morrison stood among the blade fragments scattered across frozen Nebraska soil, his scientific confidence shattered by metallurgical reality that European critics had predicted with devastating accuracy, understanding that American industrial reputation hung in the balance of his ability to solve temperature-related brittleness that had exposed fatal flaws in work-hardening steel technology.